Okay, this is the electrostatics review. We're going to do these questions, I think number 6 as well, off of there. And hopefully this helps a little bit. We'll start with number 4. Number 3, there's a typo on. It gives you nanocoulombs and microcoulombs, both in the same problem. Use nano to get the right answer for number 3. All right, number 4, the next problem then says 3 charged particles are placed in a line as shown. So let me draw this real quick. So you have this image here. We have these 3 charges placed at these distances. Part A says find the magnitude and direction of the force on particle A. So particle A right here is going to have 2 forces on it. It's going to have a force from this charge right here, the 29 microcoulomb, and also it's going to have a force from this one. So we need to combine both of those. So let's find both of them individually. So let's first find the force of B on A. I'm going to write it like that. So that force is K Q1 Q2 over R squared, where K is 9 times 10 to the ninth. So if you fill the rest of it out, you get this. You plug in charge from B, charge of A, and the distance between them. Make sure you use 0.35 meters and not 35 centimeters. When you evaluate that, 43.4 newtons. Then we're going to do the force of A on B. It's the same exact formula, only this time we're going to use this charge and this charge. So I'm going to plug that in. Actually, it'd be C on A. And then we would plug in C and A for those 2 magnitudes right there, and the distance between them is 0.54. If we evaluate that, we get that numerical. Okay, 10.3. So now what we need to do is we need to figure out what direction these are going. So obviously this negative one is going to be attracted. So it's going to, the force from B on A, the first one we found, is going to be positive. If I call this the positive direction, this the negative direction, this would be a positive, or to the right. But this force, 10.3, is going to push it to the left because those are like forces, so I can call that left or negative. And I do want to then add those together. Part B says find the magnitude direction of the force on particle. For part A, if we want to find the total magnitude, we got to add these together. So I'm going to subtract 43.4 and minus the 10.3, and that gives me 33.1 newtons, right? And this should be 0.895 right here. Because the distance between them, we were supposed to add these distances, get distance between A and C, which I didn't do. So make sure that's 0.85. It does give you 10.3 newtons, though. All right, so we're going to skip part B then because it's very similar. Let's move on to number 6 then. Number 6 says a particle with a charge. So we're given the charge of this particle is 1.01 times 10 to the negative 6 coulombs. And it gives us another particle, I'll call that Q2, has a charge of 0.907 times 10 to the negative 6 coulombs. And it gives us the force that they exert, which in this case is 4.56 newtons. And it wants to know the distance in between, r. So we're going to obviously use Coulomb's law. K Q1 Q2 over r squared is the force. So they give us everything we need. I'm just going to plug these in. 4.56 equals 9 times 10 to the ninth times. Okay, once you plug everything in, now we can just solve for r right here. Now solving for r, you just multiply both sides by r squared and then divide. So, and take the square root. I think you guys can handle that. And then you get 0.0425 meters. Okay, the next problem is number 7. Number 7 gives us these 3 charges located here. And I know it gives us centimeters here and it gives us microcoulombs, but I flip this into coulombs and meters so we're in the right units. It tells us this is a 90-degree angle as well. And it wants to know the magnitude and direction of the force experienced by particle B. So we're going to isolate particle B, and we're going to draw a free body diagram on particle B right here. We've got 2 charges, or we've got 2 forces that are exerting on particle B. We've got the force from charge C on charge B, which would push this way. So I'm going to call that the force of C on B. And we've also got the force of A on B. Actually, this would go the other direction because they're attracted. So this would be the force of C on A. And then these 2 forces are opposite in sign as well, so they're attracted. So I'm going to also have a force pushing up, and I'll call that the force of A on B. All right, so I've got those 2 forces. I want to figure out the magnitude because the resultant then of those 2 forces is going to be the diagonal right here of the parallelogram that we can make. Or if we just move this one over and make a triangle, and call this the force of A on B, we can just do the Pythagorean theorem and inverse tangent to find that angle, to find the magnitude and direction. So the first is I'm going to have to do Coulomb's law on both of these forces right here. So go ahead and plug in, for the first one, force of C on A, you're going to use this for Q1 and this for Q2, or vice versa, and use this for R into this formula. And if you do that, you get 0.252 newtons, and that's the force of C on B right here, not C on A. Then you're going to do the same thing. So I'm going to write that right here, 0.252 newtons. And then we also have the force of A on B. You get 0.045 newtons for the force of A on B if you plug in A in for Q1, B in for Q2, and the distance between them, which is, sorry, not the 29, but the 0.21. So now we're just going to do the Pythagorean theorem and inverse tangent with this. The Pythagorean theorem of A squared plus B squared equals C squared gives you 0.26 newtons. And then if we want to do tangent of theta equals opposite, 0.045 over adjacent, 0.252, and do inverse tangent of this right here, we get our theta, which is about 10 degrees would be our angle. So our overall resultant magnitude would be 0.26 newtons at 10 degrees. And that angle we can represent 10 degrees above horizontal to the right. And that's good enough. Alright, so here's number 9. It gives us an equilateral triangle here. It says 3 point charges are placed at the corners of this equilateral triangle that are 0.05 meters apart each, or 5 centimeters. And it tells us that the magnitude of the charges is all the same, which is negative 3.4 times 10 to the negative 6 coulombs. The question is, what's the resultant magnitude of force acting on one of the charges? So let's choose A. Let's draw a free body diagram for A. There's two forces acting on A. There's a force that's pushing it to the left, which we can call the force of C on A. And there's also a force that's pushing it down in this direction, and that would be the force of B on A. And we also know the angle between there. For an equilateral triangle, this is a 60-degree angle. So if you were to extend these lines, this would also be a 60-degree angle right here, because those are vertical angles. So I'm going to use this triangle right here. And I can make a parallelogram out of this using the parallelogram rule. The resultant that I want is the magnitude, which is the diagonal of that parallelogram. So that's what I need to find. And I need to find these magnitudes first. So I'm going to use Coulomb's law, which is K Q1 Q2 over R squared for both of these. If I do Coulomb's law for the force of C on A by using both charge A and charge C here, and the distance between them is 0.05 here, should get 41.6 newtons. And then you can do that for both of them. So they're both the same, because we're talking about the same distance and the same amount of charge, which means that that these sides are the same. So actually what I've made is a rhombus, which is actually helpful if you remember your properties of a rhombus from geometry class. Then you know that these angles are the same, which are both 30-degree angles. Now, for finding this magnitude right here, we could use the law of cosines or the law of sines to find this, because in a rhombus, that's 30-degree angle. This is an isosceles triangle, so the base angles are the same. And also then this would be 180 minus 60 gives you 120 for that angle right there. So if we wanted to use the law of cosines, it's c squared equals a squared plus b squared minus 2ab cosine of angle C, where side C is what we're looking for, and angle C is the big angle here. So side C is what we're looking for. I know the sides of both of these are 41.6. And then obviously 41.6 goes in for A and B here as well. And the cosine of angle C, which we know is 120. So all we have to do is solve for this C right here. Now I'm assuming you guys can do this math in your head, or I mean not in your head, but with your calculator, and then square root both sides of that equation to get C. And if you do that, you get the magnitude 72 newtons, about. Next question, number 11, says how far apart will two electrons need to be to exert a repulsive force of 1 newton? So we're just going to fill out Coulomb's law with the electron. These are 2 electrons, so I'm going to put the charge of an electron in here. 1.6 times 10 to the negative 19 is the charge of an electron, coulombs. So that goes in for both Q1 and Q2. And then the force we said was 1 newton here, so just plug everything in. You know that K is 9 times 10 to the 9th. And you're solving for R in this case, which hopefully you can do. Let me just write this out. I would multiply both sides by r squared to make this r squared and cancel it from the bottom. And then just take the square root of both sides. So this is what you end up getting. 1.5 times 10 to the negative 14 meters. And then the last problem, 12, gives us two pith balls hanging from the strings of length L. They both have charge Q. They make 30-degree angles with vertical, and they're 25 centimeters apart, or 0.25 meters. I could then draw a free body diagram on one of these. I'll do it on this one here. We've got tension pulling up this way, so I'll call that the force of tension. And that angle's 30 from vertical up here, which makes it a 60-degree angle down here. And then we have the mass pulling straight down, so I'll call that mg. And then we also have a force pushing to the left, which I'll call the force of electricity. Electric force is really the force between these two charges here. So there's our free body diagram along with our regular diagram. Part B then, it says, what is the charge on each pith ball if the mass that they give us is 0.005 kilograms, or 5 grams. Okay, if I know the mass is 5 grams, if I multiply that by gravity, I get this quantity here, which is 0.049 newtons. I know then that if I break tension up into two components, the one along the x and the one along the y, I know the y one has to be 0.049 newtons because these forces have to be equal and opposite to be in equilibrium. So if that's the case, I can use, tangent equals opposite of adjacent. So I can do tangent of 60 degrees equals opposite 0.049 over adjacent x. Multiply both sides by x and divide by the tangent of 60, and you get 0.028 newtons about. That's this force here, which has to be equal to the electric force because those have to be equal and opposite. So now I'm going to set the electric force, which is equal to k q times q over r squared, where we know some of these values. The force now is 0.028 newtons. Q is 9 times 10 to the 9th. We're looking for the charge. They're both the same. And divided by the distance between them, which is 0.25 squared. So we're solving for that Q. We want to multiply both sides by 0.25 squared and divide by 9 times 10 to the 9th. Then take the square root, in which case you get about 4.4 times 10 to the negative 7 coulombs. Okay, and then part C is the last question. It says, if the charge on one pith ball is doubled, what will be the angle of the string? Okay, so if the charge on one pith ball is doubled, so let's say it's this one right here. We double that. Well, obviously it's going to double this force because we can pull the 2 out. And we're going to see that this whole quantity is twice as big now. So we've got double the force. So that means that if we've got double the electric force, we have double the x angle here. Or the x thing we had written here. If we have double that, we have a new triangle, which I'm going to draw here. So this y stays the same, 0.049 newtons. This is doubled, which is now the 0.028 right here times 2. Which gives you 0.0565 about, 0.566 about newtons. And now I can just find the new angle. If I want to find this angle here, I'm going to give the same angle that they gave us originally in the problem, 30 degrees, which is the angle up here. So I'll call this theta up here and use that instead. So we'll do tangent of that angle theta equals opposite 0.0566 divided by adjacent 0.049. Do inverse tangent to find that angle, and then about 49.1 degrees for part C. Alright, I hope this helps.